I'm going to continue to answer practice question 3 from the week 2 questions, and recall the first segment had finished halfway through us answering question 3 part F. At this point we'd got to a question talking about the central limit theorem. Now before we specifically talk about that, I want to go and show you another spreadsheet that I've created. Now here I have produced my own population of values. There are 50 of them, and those 50 elements which form part of the population are shown here in this graph as blue dots. So I think I had actually randomly selected these from the normal distribution and then rounded them, and it doesn't look too dissimilar to a normal distribution. I think if you squint a little, we've got a tail here coming to sort of like a high density region here, and then slowly tapering off to a smaller tail down here. At least it looks largely symmetrical, and it does look like most observations are in this kind of range here. And in fact, I've calculated what the mean value is for this population. It's that orange value down there. So for these blue dots, their average value is just a fraction over 60, 60.42 in fact. Then over here, I am asking Excel to randomly select 5 different values from the population. And if you're interested, you can go and have a look at the function that I'm using here. It's just randomly choosing a number between 1 and 50. So that's happening in there. Then it's going and looking up that index value, so let's say 9. It goes and looks that up, and then I've asked Excel to tell me what the corresponding value is here. So that's this formula here. You can see this VLOOKUP, which is actually very commonly used in accounting and finance. And then I've also asked it to look up the next value here, which is that one there. And that specifies, is that the first observation of 55 that we had, the second one? In some cases there are 3. So let's look at this sample here. So it's taken the 44th observation way down below here, which was a 35, one of the minimum of this distribution, and it actually picked the second one. So that's that one there. Next one, index I, so that's 55 that looks here, and the first observation 55, and the other, well in fact 2. There's a bit of a quirk in my calculation here that it's randomly selected the same value twice. In an ideal world I wouldn't have been able to reselect the same thing. But it doesn't really detract from the story I'm about to tell. So I've selected 5 values, and then I've calculated the mean of those 5 values, and that is shown on this yellow dot on the horizontal scale, and you can see for this particular sample that it was a little bit less than the population mean. Now I am going to press F9, and this is going to randomly select another sample of 5 from the population, so you'll see it changing, these values up here changing, and you'll also see down here that the yellow dots will now show different elements from the population being sampled, and we'll probably see this sample mean shifting. The population mean won't change, and nor will the blue dots. So I'm going to hit F9 now, watch what happens. So the new set, all of them very close to the kind of middle, and the sample mean I think shifted up very slightly. I'm going to hit F9 again. Now it's selected a cluster of observations that were all above the population mean, and look, the sample mean jumped from down here to quite high for this particular sample. Now I'm just going to hit F9 repeatedly, and what I want you to do is watch what happens to the sample mean, this little yellow dot down here, and in particular look at where it tends to fall and how far the extremes are. So what seems to be the minimum value that you can observe and the maximum value. So far we've got a maximum in around 67, in fact 66, I can see it up here, and we saw like a 57, 58 as our lowest so far. Okay, here come a lot of F9s. It's quite a lot of fun, and once you start doing this it's pretty hard to stop. but I will stop. Oh, now that sample gave us a sample mean which was very close to the population mean. But I think what we saw was that the sample means did jump around all over the place, but they didn't tend to get too much below this kind of region, and they didn't tend to get too much above this kind of range, and the majority were probably sitting in this kind of range here. But notice that despite the population going way out to here, we never saw a sample mean that got less than 50, and we never saw a sample mean despite an observation out here towards 90 that got above 70. Now the reason for this is that the sample mean is a smoothing calculation. If you have a very extreme value from the population, in your sample you're likely to see some other observations that aren't as extreme as that. Like this one that we're looking at now, there's this one extreme observation to the left, but that's being balanced out when the sample mean is calculated by all these high sort of observations that are just a little bit higher than the mean. So the sample mean calculation, because it averages values, in this case across 5, extremes tend to be smoothed, and so the sample mean doesn't deviate as much as the population mean does. And below this graph here, I've drawn something which I'm calling heuristic probability distributions. I've drawn them as continuous, even though my population was in fact a discrete one. But if I assumed that this population was continuous and that there were a lot more observations, but it had the same mean as up here and the same standard deviation, this is the normal distribution that I would come up with. And you can imagine just overlaying that distribution above the points there. It doesn't look like a bad approximation of that discrete distribution that we can see up there. Now the orange is theoretically the what the probability distribution would be for the sample means that we were calculating. And notice that we saw that we didn't see in our sampling any sample means that were below 50, and this probability distribution suggests that we shouldn't have expected to see very many either. And also we didn't see too many above 70. That's what this probability distribution is suggesting. But our observations were fairly dense in this region here. Now, this orange one is the probability distribution for sample mean calculations when we have 5 observations in each of our samples. And this thing here is in fact the heart of the central limit theorem. And seeing as I've talked quite a lot here, I think I'd better defer the final consideration of question 3 to a separate video. But we'll follow on from this graphical view to actually formalize the central limit theorem and then move on to finish answering question 3.